on an example. But that's important. That's another thing we would use flow net for. We definitely don't want the dam to be picked up and carried away.
This is all for earthen structures, right? You said that?
Well, they could be concrete, they could be steel, but the point is, what I care about is the flow through the soil, okay? Or rock, but we're talking about soil. Next, why don't we compute the hydraulic gradient at A? We're going to have an estimate of this now. Okay? So,
could you explain that concept? The hydraulic gradient, what I means?
Yeah. And this goes back to your question. Hydraulic gradient is the amount of energy that you lose over a given distance. So, which way is water flowing?
That way. To lower.
This way. Do you see the little arrows, the way they're pointing? Those are called flow vectors. So they represent flow. So starting on one side, I have a total amount of head. And as I flow in the direction the water wants to go, if I arrive over here, what happened to my head? It decreased. I lost some head. I lost some energy. So that amount of head that I lost is the amount of head that goes right here. And the length that drop of water had to travel to lose that head is the length that goes right here. So let's do an estimate, okay? What I want to do is, in order to estimate the hydraulic gradient at point A, I want to kind of create bounds on either side. So I would use a scale for this. Since I don't have a scale of this hefty size, I'm going to use my Mr. Bean approach. And I'm going to try to estimate, so this is 10 feet. So I'm going to estimate maybe 5 feet right here. All right, ready? There's my 5 feet.
Narrowed a little bit.
No.
Maybe you can use the marker.
Okay. Does that look about right? Why did I do that? Well, because it's a known distance. It's a known length that I know. So water is going to travel from this point right here. And it's going to travel down through A until it gets to that line right there. And A is right in the middle of that. So what's the length of that line right there?
5.
We know that
Are you
precisely.
a small angle
right?
approximation here, or?
So we know that that's 5 feet because I measured it precisely with my Mr. Bean method. What's the head right here?
29.5.
29.5. What's the head right here?
29.1.
About 29.1-ish. Does that look about right?
Yeah.
Okay. So how much head did I lose?
0.4.
0.4. 29.5 minus 29.1. So my change in head is about equal to 0.4 feet. And how much length did the water travel to lose that head?
5 feet.
5 feet. So what is my hydraulic gradient right there?
Different.
Oh, wait.
Units?
None.
None. That's right.
So you can find the hydraulic gradient from going from also like from your total head down that way and then finding that total length, or do you just want to do it in between those two equipotential
Well,
lines? Could you do it that
Oh,
way
that's
as
a
well?
good question. So what if I went an equal distance over here.
Yeah.
And an equal distance clear over here. Could I estimate that same head? Could I estimate the hydraulic gradient from that length? I could. Is that fun? What's the challenge with that? The length, measuring the length.
It's gonna be less precise because it's like you're looking at more.
You'd have to, yeah, you'd have to try to match the exact path of the water molecule, right?
Yeah. So to get a
Okay.
precise solution, I would take an infinitely small length, right there, and evaluate the change in head over that infinitely small length, right? Computers can do that. So in a FlowNet, I can click on any point, and it will say, this is your gradient, this is your gradient. Can you kind of see those nodes in there? I could click on any one of those nodes, and it would tell me what the hydraulic gradient was at those.
So why did you go past point A if we wanted to know the gradient there? It's like, you had like a full 5 feet from.
Yeah.
Well, I went 2.5 feet on either side.
Okay.
A's got to be in the middle of my measurement.
Um,
If I don't want to do this, measure 5 feet from like here to here, because A is at the beginning of that, not in the middle. So when you measure a gradient, you want to measure, you want your distance to be equal on both sides of your point that you're measuring. You want your point to be right in the middle of L. Okay?
Okay. That's what I didn't get.
Jeffrey,
Yes, sir.
is this clear? Making sense?
Mhm.
Okay. Good. I just want to make sure, because one of your questions you had was I. This
Makes
is
a lot
I.
more sense now.
Okay, very good. So, where is I the greatest in this particular format?
It's gonna be right near that sheet filing, right?
Why? How do you know?
It's the shortest
The
distance
shortest distance.
for the same interval.
So, this distance, how much head do I lose from this line to this line? The same as from this line to this line. Right? But what's the difference? The length is so much shorter. So if I have, say, 0.5 right here, but I reduce that length in the denominator, what does that do to my gradient? It increases. So typically the location that has the smallest little flow element is the location of the highest gradient, which is why that arrow is so large right there. Flow vectors change their size based off gradient. That's why these ones are a little bit bigger than like these ones that are over here. That's kind of how those work. Caleb?
Does knowing the maximum or minimum gradient tell you much? What does it tell you, I guess?
It tells you where you're going to potentially have problems. If there was going to be erosion and piping occurring anywhere on this, where would it occur?
Right there, at the final.
Right there around the edge of the sheet pipe.
But how does that, I guess in my mind, I don't understand. It would erode even though it's buried underground. I can see like erosion happening like when it's coming to the surface. But I don't really picture how erosion would happen when it's...
Oh yeah, I mean, if they're fine-grained soils, for instance, they could just carry the fines right through the pores, the void space in the soil. And then it creates larger void space, which increases the flow, or increases the velocity, which carries more soil. And so it starts just eating, creating its own pipe from within. That pipe gets bigger and bigger and bigger until it eventually makes its way. They usually actually work backwards. They're really weird. It's almost like an invisible gopher just making a burrow through the soil. And they literally are. They're like holes. Willard Bay, about 8
the